Right, I'm going to power through these questions because quite a lot of them are very similar to the instruction video and they're really a lot of maths. So first one here, write out the binary for 88 in 8 bits. So you should be able to confidently do all this now. And then you go, okay, no 128s, 164. So that means I'm left with, oh, that's like I left with 22 because 88 minus 64 is 22. Obviously, I'll spend more time than this doing this, but I can obviously do it in my head. So I've got 22 left, and I'm basically, I mean, at this point, I just look to see what adds up to 22. So I know that 16, 4, and 2 add up to 22. So I've got to go 1, 0, 1, 1, 0, and then obviously I'll just condense all these down because it's a nice 8-bit binary number. And there you go, just check that's right. So that is 2 plus 4 is 6, plus 16 is 22, plus 64 is 88. Right, there you go. Can't go wrong with that one. A medical system is an analyzing blood test results. They can get 9 options from the test. What is the minimum number of bits required to store each test result? Right, so the point of this is they can get 9 options back. So how many bits would it need for us to do 9 options? So 9 options is 0 to 8 because that's 9 distinct results. So if we were storing this in a database, you could do, result 1 would be 0 because computers start at 0 and all the way up. So the 9 options would be 0 to 8. So then you've got to think is, what is the minimum number of bits we need to store 8, the number? And the number 8 is 1000, and so we need 4 bits. Okay? I know this is a lot of kids get this wrong, but it's actually quite an easy question. They're saying basically, how many bits do I need to do a 9? And they'll be tricky. They won't be as good as this because they won't give you this leeway. What they'll do is they'll pick one like 7 so that you can't accidentally get away with writing 4. And a lot of people will write, because they'll do 8 options. Sorry. Let's say it was 8 options. Well, that's 0 to 7. And a lot of people will write 4 bits because 8 is there. Right, but actually you can get 8 options with 0 to 7, and so that would only need, so what you need to do is write the number 7 out, and then you've got, right, okay, that's 1, 2, 4, that's 3 bits, so there you go, 0 to 7. So that's another thing to be careful of. Perform a binary shift of 3 to the right. Okay, not difficult. So I'm actually going to cheat. I'm just going to take the 3 to the right are going to go, bye bang, and then I fill in because I'm moving it to the right. I fill in from the left. Because, so you think about it, if I try and line these up, they're not perfect. There's this tab. There we go. It doesn't really work that way because it's not a set size font. But you can see that these 3 are dead, okay, because they have been pushed off to the right. So I could put them here if you want, but don't do that in the exam and leave it. I mean, you might do it in your little, drawing, but obviously in the final one. And then I've added 3 zeros at the top. I'm going to get rid of that. What is the impact of shifting a binary number 2 to the right? Shifting a binary number, great spelling, 2 to the right would perform a division of 4 on the number. However, it will round down any decimal answers. For example, you could give an example, or we could. So let's think. So 13 shifted to the right twice would be 3 because you divide it by 2. I mean, you can divide it by 2. If you shift it by 1, you would lose it straight away because there's a 1 on it. So yeah, because divide by 2, that would be 6, and then 6 divided by 2 would be 3. So that's rounded down. Okay, there you go, perfect answer. Convert F3 from hexadecimal into binary. Okay, so F3, do them as 2 separate individual ones. F is 15. Okay, which is 1, 1, 1, 1. At this point, you should start to know the binary for things. What I mean is, I'm not saying you know them off by heart like I do, but just know that, I mean, first of all, it's F. It's the highest number you can have in hexadecimal, so it must be 1, 1, 1, 1. But just also know, you do 1, 2, 4, 8. Obviously, then you'd work out that's 15. I'm not going to do that because I want to speed up. So 3 is going to be 0, 0, 1, 1 because it goes 1, 2, 4, 8. And so that would obviously be your answer like that. You don't need that bit. But obviously you can have working out. What is the largest number that can be stored, good English, using 6 bits? So this is another way. This is sort of similar to this question up here, but the other way around. So all you've got to do there is just write out 1, 1, 1, 1, 1, and then add it up. Okay? So it's not difficult. You add it 1, 1, 1, 1. So that's 1, I'll space it out like this so we can add it up. Okay, so that is going to be 32, 16, 8, 4, 2, 1. So that's 31 because all these numbers always add up to 1 less than this. So actually, if you know the next number is 64, you know that 1, 1, 1, 1, 1 add up to 63, but let's do the math anyway. So that's 3, 7, 15, 31, and 65. Okay? No, 63, sorry. So this is 63 would be the highest number, the largest number. Now, I've put that one deliberately because it might bluff you. The largest number is 63, but if they say how many options there are, it's 64 because you would include 0. The largest number is 63. Add these binary numbers together. Let's do this quickly because I basically do all this in the video. And then this is going to be my carry row and this is my actual result. You should always, unless you're really, you know, I obviously don't bother, but, you know, you should write out your 2-digit version. So, you know, I mean, I don't really think at this point you probably should be able to not to do that, but I'm just going to make some space. I'm actually going to delete these, everything from here just to speed this up. Right, so these are my cheat sheets. So that's my carry, that's my result. 1 plus 1 is 2. 2 is 1, 0. So 1 in the carry, 0 in the result. 1 plus 1, 0 plus 1 plus 1 is 2. So 1 in the carry, 0 in the result, and keep going. 1 in the carry, 0 in the result. This is going to get boring really. It's the same thing again. 1 in the carry, 0 in the result. Hurrah, we got a different one. 1 in the carry, 0 in the result. Hurrah, we get a 3. So that's 1 in the carry, 1 in the result. And then, because it's 1 in the carry, 1 in the result. In fact, I could highlight all these yellow if that really helps you in some way. Probably not. I've done it now. So that's my carry. And then 0 plus 1 is just 1. So that's 0 in the carry, 1 in the result, and then 0. And then, of course, this is your final answer. Let's assume the answer box is there. Text only. Oh, I've got tabs. How annoying. But there we go. So that is my answer. You could check it, but I'm just going to presume it's right because it is. So, explain what an overflow is with binary addition. An overflow occurs when the result is larger than the block of data allocated. So I might write that a bit better. Result is too large to be written using the number of bits allocated. For example, if we added up 240 and 30, we get 270, which cannot put in 8 bits. We get 270, which cannot be shown in 8 bits. So we would get an overflow bit. It's actually a flag that ticks up. The computer knows it's been overflow, and it deals with it in whatever way it wants to do. Right, so there you go. Another reason why it's better to have like 16-bit computers, 32-bit computers, 64-bit computers. It's not that 8-bit computers couldn't do bigger math, but they have to chunk it in small chunks. So they have to do like smaller little operations one after the other. But obviously we've got 64-bit computers now, and they're big numbers. But still, you need like 256-bit for like encryption and stuff. So, right, there you go. That's the questions for this section, part B.